Hello everyone, my name is Alena and I'm very excited to be here, and today I'm going to talk about challenges of microservices architecture and share my team's experience with it. So this presentation is available on slides.com, so if you follow this link you may be able to watch it live on your laptops. So I will tell a little bit about myself and the project that I work on. And then this presentation is divided in 3 parts: architecture, testing, and deployment. So I'm a software engineer in Cisco. I worked there for 3 years in research and development team. And we have a lot of innovative projects. And for 1.5 years, I have been working on a project called Megan, which is a cloud-based data lake prevention software. We're building a flexible yet robust platform that is represented as a set of APIs for a middle layer between any cloud application that works with sensitive data, like Box or Dropbox, and securely operates with it. So currently we're already integrated with Box, and we're working on the desktop integration with Dropbox. Our use case covers using Box or Dropbox credentials, encryption of a data file with our ingestion and key services, and management of the permissions to the file based on the variety of policies that are specified by the owner of the data or the super user. Megan also offers its own identity service, so it can function as a standalone application. Recently, we have come to open source. Our code is available on GitHub. You can find the link on the slide. The main purpose of to open source this project was to give developers an opportunity to not only integrate with our system, but also secure their businesses and build a community around data security solutions. So architecture. In the beginning of the project, we had very limited time to deliver our first MVP. So after a relatively small work on design, we jumped right into coding. We had written a bunch of code, had it stored in one single repository, and got it containerized by creating a few Docker containers. But soon enough, we started to feel limitations of such approach. So from what I've seen, this is a common way of modern development, especially in young projects. It grants certain benefits. You always build in a clean environment. User space is not affected much, and containerization gives you opportunity to not care about cross-platform issues that frequently can restrict us from using cutting-edge technologies and tools. So containerization is a good start, but it is still far away from great, flexible, and lightweighted microservices architecture. But let's take a look at microservices more closely and see what benefits do we get and what challenges do we face when choosing microservices over a monolithic experience. So first of all, microservice is an independent component of the big system, and as opposed to containerized monolithic applications where those are tightly bound together. It was to mention that containerization may or may not be used for microservices implementation, and people tend to equal Docker to microservices, and which is not necessarily true. So a microservice is responsible for an undivided task, and it should be as simple an implementation as possible to represent the domain context it owns. So with this principle, we get certain benefits. Services are small enough to grow independently and enough to do fast and frequent iterations. It means we have less legacy code, we have better code coverage. The scalability is one of the strongest benefits, and with modern tools, orchestration tools like Kubernetes that offer us containerization as a service, we can create many containers per microservice and distribute the load across them. The troubleshooting also became easier. Usually errors are localized to one service, so both investigation and bug fix can be done much faster. So microservices give us a good style of development. We can ship our products faster due to flexibility and scalability that we obtain. But on the other hand, we create new kinds of problems that we didn't face with monolithic projects. So the complexity of communication between services migrated from inside the code to outside. And we have to perform it now through REST API or message buses. We also want it to be secure. We only want our service to be able to connect to only trusted services on our system. And this is a big challenge. The monitoring system also must function in new circumstances of constantly dying and respawning services. And most modern tools are not, most modern tools are not developed to this level, and frequently developers on themselves have to configure and administrate them appropriately. So microservices are very much independent now, which gives us an opportunity to use different technology stacks and even programming languages for their development. It makes it harder to standardize operations and development lifecycle for them. So microservices require some additional skills from a developer. Basically, you now have to be an administrator, you have to care about security, you have to think about scalability from the whole beginning, and operations come to the development very fast. So it requires a lot of responsibility. And let's take a look what we had back in the day. So as I said, all of the code was in one single repository, which became a problem for us very quickly. For each Docker container, S1 to S4, we had to volume whole chunk of code, which meant that each service owned everything else, and there were no boundaries. Utilities, core libraries, API libraries, integrational test suite, operations were all in one repository. So the interaction between components was one of the biggest problems that we faced. They partially used REST API, the public REST API, which was not really good, the same that clients would use. Also, nothing was preventing them from using libraries of other services directly and make a calls to the infrastructure of other services. And it meant that we easily could face the race conditions, and we would endanger the database integrity. So making functional changes to this infrastructure was extremely dangerous, and we were in a very fragile state. So we decided how we were going to move forward and how to break things down, and and to change our architecture from looking like this to look more like this. Okay. In this diagram, we can see that all of the services are now very much independent, and each service only owns itself. We wanted to make sure that our services communicate securely through REST, their operations are standardized, and that each service stores only the code that is connected to its implementation. So we came up with several steps. The first of all before making any functional changes, cover services with independent test suites. The coverage should be higher than a certain bar. For us, it was 85%. Then break the system down into several repositories. A number of those repositories should be more or equal number of the services on our system. So every service shall be a package with correct versioning. We work with semantic versioning, the major, minor, patch. The stable and latest versions must be stored in a package manager. And as you can see on the diagram, the core libraries is the center piece. So they should be abstracted and used by other microservices. But they cannot be replicated to each service. And since each core library can be easily packaged up, we use Python and Python builds. So in a native environment, it's quite easy to install them as dependencies and use directly from the code of all of the services. But with containerized environment, with Dockers, where space is no longer shared, this step should be repeated for each service. So we wanted to standardize and abstract this process as well. And we decided to create a base Docker file which shared standard libraries and core dependencies. This has not only gave us an unified approach for installation, but also increased our building speeds for containers, because heavy process of installation the dependencies was done only once inside the core repository. But this is, okay, so this is a base Docker image. So this to the left of you is a Docker file for core. You probably can see that it's based on Ubuntu 16.04 core. We're installing the standard libraries there and also installing the Maven dependencies. And to the right of you, you can see the build scripts that make sure that only latest versions go inside the base image. So recently we decided to move to Alpine Linux image, which is much more fast. And they have rewritten the C standard libraries and they have created their own package manager. The performance is very great, although if you depend on the implementation of C libraries, you might face some errors and issues, so just be careful with that. So this one now is a services Docker file, and we see that it's inherited from Maven Docker, Maven Core. And there is no installations of the dependencies anymore. Only the installation of this particular wheel that we want to install and for this microservice. So in order to standardize the operations for services, we had to store them in independent repository as well. But unlike core libraries, build and test operations have to work with services code directly. And meaning that they have to be stored per service. So the best solution that we found is to use Git submodules, and submodule would be used in each service. So those Git submodules, they allow you to work with the code repository directly, and at the same time instantly push the new changes to the services. So this is, you can see these the services Git repository, and it is reference to an operations submodule to particular commit. So those operations contain Docker operations, unified make targets for building, running, testing, both natively and inside the Docker, uploading scripts for continuous integration and delivery. So all of these steps help us to make our system more decoupled and flexible, and also calls to the importance of setting up the continuous integration. Now we have very much independent services, but then still depend on core libraries and operations. So on each change of those two, we must make sure that the whole system stays functioning. Another important step is to establish a secure connection between the services. And how to make a service be able to connect to only trusted services without affecting its implementation much. So let me introduce you to SPIFFE, which is a security production identity framework for everyone. It's in very early stages, and SPIFFE proposes a new set of protocols and conventions to secure communication and identify service-to-service communication in modern production environment. It's aiming to provide a security specifically for microservices, and as opposed to microsegmentation, where network is programmed in a special way to only allow traffic from between specific endpoints. SPIFFE offers a more flexible approach. So with microsegmentation as a part of describing and running a service, the user would have to also describe an endpoint that is going to send or receive network traffic from. And this approach has certain limitations. We have now a pre-configured network. We are unable to work in a moving environment, and in microservices world, services should be able to invoke a secure connection on their own on every run. So SPIFFE stands for establishing a TLS connection between the services on runtime. And SPIFFE aims to provide all the operations to each service, so it easily can obtain two things: a set of certificates to endpoints that it's going to access to, and a set of root certificates with data to what services they apply. So this is Spire. So this is Spire. Spire is a spiffy runtime environment. You don't actually have to see the whole thing because this is a slide from the demo, and it's not quite a response to what Spire actually should do, but it's the very early stages of development. It's an alpha project. So basically, the Spire wants to create a Spire server, and you see it there as a green block. So this Spire server has a certificate authority that can issue certificates to all of the services on every run and during the runtime. So then a service that obtained all those certificates sets up a TLS connection or uses a ghost tunneling or a proxy to set up the TLS connection between the services. And the nice feature is that service discovery also is happening via Spire server. Servers can call out to other services by the name that they are registered in the certificate, which is really cool. So more information you can find on spiffy.io. The development, as I said, is an alpha stage, and we are willing to contribute to this project and develop a workload API in Python. And we believe that this project has a big future. It is also supported by Google and LinkedIn, and I hope you find it useful and interesting. So these are the main steps that we wanted to achieve, and we have succeeded with most of them. Some of the work still remains, but this is what we have today. We have 8 repositories in total. 6 of them represent microservices and 1 represents operations. We have open sourced 7 of them. They have good code coverage and continuous integration enabled. And the whole transition took us about 2 months. So far we have discussed architecture that suits our use case and steps to be performed in order to achieve our goals. And one of the most important parts, a key piece that makes development lifecycle easier and stable, is testing alongside with continuous integration. So in the world of microservices, we can no longer have an integration test suite for all components or system test without making sure that all our services function properly standalone. So in order to ensure that a service behaves correctly, code coverage must be increased, and it's hard to achieve the highest coverage by applying the same testing strategies to all layers of the service. And Martin Fowler, in his presentation about testing microservices, offers to combine unit tests, integration tests, and component tests. And unit tests are divided in 2 parts, solitary and sociable. And solitary tests are independent unit tests with mocking everything that is outside the testing scope. And sociable tests are more focused on modules behavior and use black box testing approaches to deliver that. So component test is very important, and frequently in microservices architecture, the components are services themselves. And in our case, I tried to apply Fowler's paradigms to our architecture, and every component, so every service has their own integration and unit test suites. And when you see those orange blocks, those are component tests with core libraries because they're used directly in the code. So microservices are built by divide and conquer paradigm, and they pursue a single responsibility principle. And this principle is successfully adopted in testing infrastructure as well. So automation of the test should be abstracted from the test implementation so it can provide necessary flexibility. Also, tests themselves must be flexible enough. With microservices, we can no longer trust blind testing when we compare 2 data sets, expected and received. And based on that comparison, we fail or succeed the test. In our environment, we use instead functions that can return some metadata with the data set. So basically it can be status messages, Boolean flags, something that we can use in testing, and it also could be useful for end user. So flexibility of test is very important and hard to achieve, since the tests tend to restrict the boundaries of implementation of the code, and at the same time, they at some point may lead to a code stagnation. So the most valuable approach is to keep them flexible, and I think that this metadata approach is really good. So with all this said, this single responsibility principle may lead to a cross-service bugs, because system and integration can discover new bugs to infrastructure. As these bugs may not have a straightforward solution broken down to a single microservices, the finding of the solution now traveling from service to service, just like a customer in a call center. And because nobody is responsible for this fix, we actually kind of slow down the process of the development. So the only thing is that we have bug that affects more than 2 services. It only means, sadly, that system is not flexible enough and that we could be broken down more. With MVPs, when it's hard to predict architecture and business requirement changes, the architecture shall be granular enough to support all the flexibility that we discussed. And functional change is better to be test-driven. When we write a test with no code implementation in place, we kind of pursue that flexibility from the beginning. So we have already discussed the importance of continuous integration, and I wanted to spend a couple of minutes why did we choose Travis CI. And at the time, we were thinking to use one of these 3, Jenkins, Circle CI, and Travis. Jenkins is a great tool, very flexible and customized tool, and I'm sure here a lot of you guys are big fans of it. So but it requires a lot of configurations, let's be honest with each other, and also the dedicated server to run. And we had very limited resources, and nobody on the team was a Jenkins expert, so we decided to pass on it. And now the choice was in between Circle CI and Travis. They are both great. They are both cloud services, and they require no dedicated server to run. One of the good features of Circle CI that goes out of the box that they have the debugging build, so you can debug build through SSH, which is really cool. And this feature goes in only paid plans for Travis. But the community customization libraries are better in Travis, so we decided to work with it. And it also worth to mention that they are both very quiet to set up. But Travis is just intuitively understandable, at least for me. It took me only 30 minutes to set up a full CI for a service. So these are other benefits that Travis has. One of my favorites is triggering builds. Using the REST API, it is very easy to trigger a build for a service. We are using this feature for core libraries and operations. Push to master of core or operations repos invoke builds of all functioning services. There are libraries in Python written in JavaScript. So the other thing is parallel builds. Travis supports a build matrix out of the box comparatively to Circle CI that has workloads, but this is way less to write as opposed to Circle CI. So please note that in commercial Travis, these parallelized builds actually work much faster than in open source, which is unfortunate. And there's also an opportunity to run your test for different versions of language or other environment, which may be very important for open source contributions. So this is also provided in Circle CI, the nice UI, and a lot of people think that Circle CI has better UI for analysis. But secrets easily can be added to Travis as environment variables. and we use it for Docker Hub and PyPy. And those secrets will be never exposed on any configurations files or any logs, which is quite cool. So this is our Travis flow. We basically have two targets, two jobs, native and Docker, and after commit, Travis CI makes sure and runs all the tests. And then if we are on a branch master, then we upload our artifacts to PyPy, Docker Hub, and AWS staging. But if we are on core and operations, we're also triggering the builds for all other services that basically just do the same thing. So deployment is the last step in our journey, and with all the steps that we performed, it's likely not the hardest one. So currently we're in a stage of continuous delivery, where actual deploy to production is happening manually as opposed to continuous deployment. And deployment pipeline flow can be achieved much faster nowadays with modern tools like AWS. And Travis, as I said, doing for us builds upload to Docker Hub and AWS and pipeline. So deployment in our case is done with AWS. We discussed already a flow till continuous integration. It's basically commit, the version control, continuous integration with Travis, and what happens then. So AWS offers its own tool for versioning control and continuous integration. Well, one of the coolest things is code deploy, which allows you to deploy automatically your code to EC2 instances. And code deploy is free and goes with any plan that you buy on AWS. So Travis is integrated with it. It allows creation of multiple deployment groups, like testing, staging, production. They may have priorities. One of the good parts also is that if you by any chance uploaded a breaking change to your environment, code deploy will stop deployment after first broken node, then all the code will stay functioning. So at most you lose one node. Our distribution is made also with AWS. We use Route 53 to provide DNS for our services, and we have a load balancer per service, per microservice, and 3 EC2 instances where we run the code. So this is a Travis configuration for delivery and deploy. The first one is deploy. You see the provider is a code deploy. So basically, the Travis can do the whole thing for us, and we just receive emails or notifications. It's very nice, and hope that they are not read. And the after success uploads the stuff. So for us, it just runs the link upload target. So this is it from me, and maybe you have some questions, and thank you.
Thank you, Alena. Thank you for presenting some information today.
Oh, thank you. Thank you.
Does anyone have questions for Alena?
Can you please show the slide with a link to the slides?
Sorry. What?
Can you please show the slide with a link to the slides of this presentation?
This one?
Yes, thank you.
Yeah. You can actually, if you don't put live in the end, then it's available all the time. You can access it anytime.
More questions? I suppose questions in Russian possible too.
Yeah.
Нет? В таком случае давайте поблагодарим Алену за прекрасную лекцию.